If you're doing VCE methods, one of the most underrated topics is linear functions and coordinate geometry. This is because all of the topics in VCE methods, pretty much after this, all are boiled down to the skills that we learn here. So it's really important to understand the skills here to make sure that we can apply that to quadratics, cubics, trigonometric functions, and pretty much all of the other topics in VCE methods. So let's go ahead and do this really basic example where we have 2 points on our Cartesian plane. And we're going to do a lot of operations with these 2 points and pretty much just understand the fundamentals of coordinate geometry. So what we can see here is we have 2 coordinate pairs. We have 2, 1 and 6, 4. Now it's really important to understand the Cartesian plane. We have x in the horizontal direction, y in the vertical direction. And when I plot these points, it's not only for these individual points here, it's whenever we plot points, even with a function rule, it's that you have to keep your axes to scale. So what I mean by that is x is equal to 2 goes to about there for that coordinate. That's how I've drawn it before. X is equal to 6 is here. And you can see that's 3 times the distance from the y-axis because we go 2, 4, 6. It's not perfect, but roughly, if you just look at it, it looks right, yeah? So you can see 6 units to the right versus 2 units to the right. It's about 3 times the distance. Same as if you look at the y direction, we have 1, y is equal to 1 for this coordinate here, 2, 3, 4. Again, it's not perfect. You can see I've got a big jump here and small jumps there, but you can see it's roughly 4 times the height. So as long as it's roughly, the y is roughly in scale with other points and the x is roughly in scale with its own points, then we're pretty much in the clear. Now, what I would say is that for x and y to both be in scale together, that's honestly a pretty hard thing to do. And the reason for that is because if the y values, for example, are really big and the corresponding x values are really small, then it doesn't make sense to try and keep those axes in scale. So I'll give you a really basic example. Let's say I draw this Cartesian plane here and we're trying to plot the point 1, 30. So if we try to keep the x and the y in scale with each other, then what would happen is that for 1 unit to the right, for x is equal to 1, we have to go 30 units up. So we go 1, 2, 3, 4, 5, 6, all the way up to 30. That's going above this video, right? You can't fit it on this whiteboard. You can't fit it in this video at all. Probably go to the roof. But what you can see is that it doesn't make sense to keep the x and the y scale, or the x and y scale is the same in this case. It just makes sense to keep the y scale in its own frame and then the x-axis in its own frame as well. So 1, 30 might be something like this. And you can see it's not 30 times the height compared to the width, but it's just fine. You can just see that you're going 30 units up. But then if we have another point, let's say 1.5, 60 or something like that, then that would be roughly here. So let's say 1.5, 60. I'm not sure how small this is on the other camera. Hopefully it's somewhat visible. But what you can see is that 1 is relative to 1.5. It's about 1.5 units, obviously. And then 60 is double of 30. So it makes sense that the y is double and then the x only goes to the right by a little bit. Hopefully that makes sense. Okay, so the whole summary of that is that the x should be in scale with itself. The y should be in scale with itself, and if you can, you keep them in scale together. But if it's unreasonable, let's say if you have tens or hundreds on the y scale versus units on the x scale, it doesn't make sense to try and keep them in scale. Just keep them in different scales and all will be fine. Cool. Okay, so we have 2 points here, 2, 1, 6, 4. It goes x, y when we read our coordinates, if you didn't know that. I'm not sure what to tell you, but that's how you read it. Okay, so with 2 points on this Cartesian plane here, we can connect a line and pass a line through those 2 points. You don't really need to know this for VCE methods, but it's good to know just for general knowledge. The connection in between the points is called an interpolation, and then everything beyond that, so let's say here and also here, that's called an extrapolation because it's going beyond the bounds of our 2 points. Now we need to have 2 points to find the equation of a line. We're not going to talk about the equation of a line just yet in this part of the video. It'll be in the next portion of this video. We're just going to focus on having the 2 points and seeing what operations or what things we can find about those points. But just keep in mind that 2 points is really key to us because not only can we do all these operations, but just connecting 2 points, we can find a straight line between those 2 points. Now, one of the key operations that we use in linear or coordinate geometry is finding the distance between the 2 points. So this would be the direct distance between them. So that's just like that distance in between the 2, 1 and 6, 4. And you might recognize the formula. probably seen it since year 8 or year 9. So you take the difference between the x values, you square that. You add the difference between the y values, you square that as well. You add them both together and you square root the whole thing. This is pretty much just, if you boil down, the Pythagorean theorem or the Pythagorean identity. So how it's actually formed is you can create a right angle triangle between these 2 points. The horizontal distance is the difference between the x values. The vertical distance of the triangle is the difference between the y values. So essentially what you have is you have your A and B, and you're trying to find your hypotenuse C. So if we do this for this triangle here, what happens? We go 6 minus 2, which is equal to 4. So we square that, plus 4 minus 1, which is equal to 3. We square that, and this is actually an exact value. It's a 3, 4, 5 triangle if you've ever seen it before. So it actually ends up just being 5. Now, a lot of the time, you're probably not going to get an exact triangle. Most of the time, you'll actually be getting surds in your answer. So just make sure that if you do get a surd, you simplify the surds down. Hopefully, you guys know how to simplify surds. If not, we'll probably just make some more basic revision videos for you guys to perfect that knowledge and refine those basic things from a few years ago. Understandably, people forget those types of things. So we're definitely trying to cater to all audiences. Nice. Now, another thing that we can also calculate is the midpoint. So midpoint here, it's literally, as the name suggests, just the middle value or the middle coordinate between the 2,1 and the 6,4. Now we could just think about it and say, okay, 2, 6, what's in between that? It's obviously 4 for the x value, but it gets a bit harder when you have odd values. So for example, if you have 1 and 4, a lot of people might confuse that and might say 3, might say 2, but it's actually 2.5. The safest way to go is just use the formula. And the formula is pretty easy to understand. You just take the x values of each of our coordinates and then you add them together, divide by 2. Essentially just finding the average or the median between those 2 points. So x1 plus x2 divided by 2, and then y1 plus y2 divided by 2. Now, x1 plus x2 will be 1 plus 4 divided by 2. And then for the y values, no, sorry, I'm getting them mixed up actually. They are the x values. Let me just fix this here. So it'll be, in this case, the x value is 2 plus 6 divided by 2, and then 1 plus 4 divided by 2. I have it in my head to not mix up the x and y values. I think I'm really over-assessing about it because just previous to this video, I recorded a set of 3 videos, and it was all based on these coordinates, right? I have 2,1, 6,4. And at the end of the video, of this part of the video, I recorded the gradient section. And then, I calculated the gradient, and then I used the same numbers to go to the next example, the next video. And then I also made a video after that. So I made 3 videos in a row, and it was all based on the first calculations. And the gradient calculation I actually did wrong. And then I was basing it, all 3 videos were based on wrong values. So I had to I'm re-recording the whole thing right now. So so I'm just, in my mind, I'm just like, don't swap the x, don't swap the y. But yeah, obviously it just happened then. I realized I did it here as well because I did the difference between the x values and then I said, oh no, that's actually right, don't worry. This one was wrong, but okay, we're fixing it now. We're getting there. See, even people like me who have had a lot of experience with maths, you can make a lot of these basic mistakes, and I'm trying to take a lesson from just making a muck up. But you can obviously, it's very understandable that you do make a lot of mistakes when you do VCE methods and just when you do SACs and when you do exams. So it's about mitigating them and taking things as slow as possible. I notice that when I make the most mistakes, it's when I'm kind of anxious and overthinking a lot of things. So it might be when things are a bit more time tight. For example, I don't have a huge period of time to record today, so that's why I might be a bit more anxious. But when I'm in a more relaxed mood and I'm kind of controlling the pace of how I do things, and it applies to tests and exams as well, I make a lot less mistakes. So that's just a thing to keep in mind. It might be the same for you. I know most of the people that come to us and say they want tutoring, a lot of the time it is because they have those 1% mistakes that do add up. And it is a true fact that they actually do add up, especially if you do easier subjects. Maybe not so much more in methods and specialist maths, but more so in further, because marks are worth a lot more, because the subject is a lot easier. A lot of people do want to focus and refine those mistakes. And the first thing I say is just, it's easier said than done, obviously, but if you're less anxious when you're taking a test and you're prepared, usually people who are prepared more end up being less anxious because they're less worried about what's going to happen. But if you're prepared more, in turn, you're less anxious, therefore you're less likely to make mistakes. And that's, the first thing that I'll say about that. That was a bit of a segue from what we're trying to do here, but yeah, we'll move on. We'll finish this calculation. 4 divided by 4 is our x coordinate. 1 plus 4 divided by 2, 5 over 2, or 2.5 if you want to put it as a decimal. Just to talk about that previous thing just quickly. We do have study tips videos on our YouTube and in our online course, so I would recommend watching them. They're recorded by Heshan, who's my good friend, who's well experienced with those types of things, and some of them are recorded by myself as well. I think it is really important to take the time to not only revise your content, but also learn the appropriate study tips and have the right mindset to perfect not only VCE methods, but just VCE in general. Cool. Okay, so we've covered distance, we've covered midpoint. These are two of the formulas that are really key to a lot of application problems. A lot of times when you do application problems, the distance and the midpoint calculations are kind of hidden in certain examples. Let's say if we have some sort of kinematics, or kinematics is pretty much like physics. You can think about it in this subject. So there might be these types of questions integrated within them where I might not say find the distance between 2,1 and 6,4. It might be more discrete and more hidden essentially. The last thing that we can calculate is the gradient. So the gradient of a line, you might not know what that is, or you probably have heard of it, but you might not truly understand what it actually means. So I'm just going to do a bit of drawing here. What we can see here is that this line here, as it goes to the right, it goes upwards as well. So we actually classify this as a positive gradient because as it goes right, you go upwards. Okay, so we call this a positive gradient. If it went the other direction like this, it goes to the left as it goes up, we call that a negative gradient. Now, positive and negative, it's pretty easy to distinguish between the two, but you might also have a larger gradient versus a smaller gradient. Now, when we say larger and smaller, it's always relative to another one, right? We don't just say, okay, this line here looks like it's pretty steep, therefore we say it's a large gradient. It's always a comparison between two. So if we have this dotted line here, this is also a positive gradient, but we would call this a steeper gradient, or one that's just higher in magnitude. So this might have a gradient of 3, this might have a gradient of 10. So you can see the value is larger in comparison to the other one. They're both positive, but one's just steeper than the other. So a steeper gradient would have a higher magnitude. So in this case, the m would be larger. So m up arrow, essentially m is larger. Now you can have a larger negative gradient. So this is also steeper, but it's steeper in a negative sense. So the magnitude is greater. So you might have -3 for this gradient, and you might have -10 for this gradient. So even though it is steeper, it's a more negative value. So we say the magnitude of the gradient is larger, but it's more negative. So I wouldn't necessarily say that the gradient or the m value itself, we use m for gradient by the way, I wouldn't necessarily say that the gradient is larger or smaller. I'll just say the magnitude of the gradient is larger in this one, or the line is steeper versus this one, but they're still both negative. It just gets a bit confusing when you say larger and smaller with negative values, because a lot of people would say that a larger negative value would be just bigger in magnitude. Other people would say that you have a smaller negative value if it's further to the left of the number line. So it's just a bit of confusion when you talk about negative values, but if you just separate between sign and magnitude, then you're good to go. You can kind of classify any line. Neat. Okay, so as I said before, m is the gradient. Now, a lot of people refer to this as the slope of our line because it's just positive, negative slope, or large slope, small slope in comparison. Now, the colloquial way that we kind of remember how to calculate a gradient or what it actually represents is what we call rise over run. Most definitely, you've heard this term before, rise over run, but a lot of people just hear, okay, rise over run, what does it actually mean? They just memorize the formula. It's good to understand what the rise over run actually means, and especially when you get to the kind of these edge cases where you have an infinite gradient, you can have a zero gradient as well. This formula really helps out in understanding what that actually means. But what rise over run means is the rise is literally just how much our line rises in that period. So this is the rise here, and you can see that's in the y direction because it's vertical, rise is vertical. And then you have the run here, which is our, I'm just going to write run. That's our horizontal movement, or the difference in the x values because x is horizontal. So if we want a formula for rise over run, what we do is we say y2 minus y1 over x2 minus x1. So the difference in the y values divided by the difference in the x values. Actually, I'm not going to do that there. We'll keep them separate. So if you want to calculate the difference in the y values, you go 4 minus 1. So this is what I stuffed up last time. In the previous recording, I did 6 minus 2 for the numerator. But no, the y value is on the top, 4 minus 1, and then you divide that by 6 minus 2. So 4 minus 1 is equal to 3. 6 minus 2 is equal to 4. So we have a gradient of 3/4, or 3 over 4. Now, what you can see is that the 4 was paired with the 6 as the leading term for both calculations, and then the 1 was paired with the 2. That's really key for this calculation because we have to keep them consistent. If we swap them around, for example, if I did 4 minus 1 and then I did 2 minus 6, you would actually get the negative gradient, which is incorrect. Or you just get a wrong answer. It doesn't matter if it's negative or positive or whatever, you're just doing it wrong. But it's okay, it doesn't matter which one you choose. I just chose the most right one because they're more positive values, but I could have done the other way around and I would get the same answer. So what I could also do is I could say 1 minus 4 divided by 2 minus 6. You can see again the 1 is paired with the 2 because they're the same. And if I do this calculation, I get negative 3 divided by negative 4. The negatives cancel out as a common factor of negative 1, and I end up getting 3/4 anyway. So it doesn't matter which one I have as my leading one, as long as the y and the x matches up for the leading one, and the one being minus matches up for the corresponding one. Cool. So we can see in this case, gradient of 3/4. Again, we can't necessarily say that this is a steep line versus if it's a more shallow line. It's more so just, okay, this is a positive gradient, has a value of 3/4. And if we compare it with another model, then we could say that maybe that model is steeper or that model is shallower. But when we have a steeper line, you'll learn this as you go, and you've probably done differentiation in year 11, but you might not really understand what it actually means. But anyway, if we have a line of 3/4, what we say is that the rate of change is 3/4. So that's another way that we kind of, we have gradient, we have slope, we have rise over run, but what we actually call this is the rate of change as well of our line. And that's because that's how fast, we kind of use a gradient to measure how fast the line is moving upwards. So if we have a line, so this is 3/4, which is 0.75. If we have a gradient of 10, then that line is moving up very fast. Compared to this line, with a gradient of only 3/4, this line is moving up very slow. Nice. So we've covered a few different calculations that we can do between two coordinates. So we've done distance, we've done midpoint, we've done gradient as well. Now, the key idea that we're kind of tending towards with coordinate geometry is moving more towards linear equations. So the gradient is our first step of constructing linear equations. But in the next video, we're going to use the same points and actually construct the linear equation and see what actually comes of the calculations that we do.